Okay, this lesson is about the equilibrium of concurrent force systems. Okay, so sounds really complex. It's a very long title. Equilibrium is just balance. So anytime you've got an object that is at rest or moving without increasing its velocity, it's got no resultant force acting on it. So in this instance here, this is probably the simplest example of that situation. Concurrent force system. We have weight force acting straight down, and we have the reaction, equal and opposite reaction, acting up. Okay, Newton's third law. So equilibrium is a condition when the force system is balanced, i.e. there's no resultant. Most force systems we will deal with are in equilibrium, otherwise they would be moving to achieve equilibrium or would fail. So we're talking about structures. Later on we'll do truss analysis. Quite often the systems we're dealing with are in equilibrium, especially when we're talking about civil engineering situations like that. So we've used a very simple example here of a book on a shelf, which is like I just described. And we have our force of reaction, F subscript R, which is going to be equal and opposite to our weight force, mass times gravity. Weight is the force, okay? Now, there's conditions of equilibrium, and these are the conditions later on when we talk about calculating moments and reactions at supports for truss analysis happening later, but this is something we need to get our heads around now so that it won't be so difficult. The conditions are no resultant force. So we can see here that this and this are equal in opposite directions, therefore we have no resultant. The force polygon closes, so whatever, when we add our vectors, and we've done addition of vectors, you will return to the starting point when you add them. If you don't return to the starting point and the system is in equilibrium, it means you've missed a force, okay? So force polygon closes, so in this instance here, one goes up, tip to tail, one goes down, and therefore the system is closed, okay? If you had a more complex system where you're adding, if you got back to the start, okay, all the way back to the start, we know that there's no resultant, okay? So the force polygon closes, and the sum of all the force components, vertical and horizontal, is equal to 0, and the sum of moments is equal to 0. Now we haven't done moments yet, but when we do, you will have to understand that the system's in equilibrium. The moments that are making something spin clockwise are going to be equal to the moments that make it spin anti-clockwise. Okay, so don't worry about that moments too much, but this is something you'll need to understand about systems in equilibrium later on. Okay, so we've got sigma. Remember that means sum of. Force is vertical 0. Sum of force is horizontal because it's equal to 0, and sum of moments is equal to 0. Now you'll use that knowledge when you do analysis, especially truss analysis, to find solutions for problems that you'll be given. So that is what you need to know. Now we'll be, on the exchange page, we'll be looking at 3 force systems that are in equilibrium and working out the resultant, the force that we're missing to create that equilibrium situation. So, you know, you might have someone pulling on a rope and an object is balanced, and someone's pulling on a rope to stop it from falling over, okay? And the whole thing is balanced, so it's an equilibrium, and you have a reaction force coming up from the ground. You've got a weight force acting down, you've got a tension on a rope holding it in position, okay? So we'll be doing that type of problem on this page, and that's why we're looking at this. So pause the video and make sure you get these notes written down, especially what's in this box here, because later on when you're dealing with systems in equilibrium, this is the information that you'll require. See you next video. Or maybe the second part of the same video. I haven't worked out yet. Okay, this is the second part of this lesson. Other stuff to remember. Okay, now I would pause the video and get this half of the board written down. And I'm just going to go over it very, very quickly. Some of this stuff is already on the side anyway, but I'm just harping on about it. When a force system is in equilibrium, the force polygon will close. We already talked about that when you're adding tip to tail. We come back to the starting point. Most force systems are in equilibrium. This fact is used to to determine the value of unknown forces. Okay, so we're going to do some of these problems, and you'll see that once you know the system is in equilibrium, you can calculate, for instance, tension in a rope of something that's holding up a weight. We're going to do that type of problem. If your result seems to not be in equilibrium, be sure that you've included all the forces. It's quite easy to forget about a reaction force that's there but they don't show it. If there are three forces on a body and it is in equilibrium, they will be concurrent or parallel. What does that mean? Basically what that means is either all the forces, if this is a weight being held up by a gentleman holding onto a rope, okay, he's holding it, it wants to fall this way, you'll have tension in the rope, that's one force. You'll have a reaction from the ground, we have a weight force going straight down from the centre of gravity, that's another force. And what will happen is, when you actually extend those lines using transmissibility, you'll get a point of concurrence, and that means you'll have also a reaction from the ground. Okay, and we'll be doing this type of problem very shortly. Okay, so the reaction from the ground is the third force, and that point of concurrence is just there. Three forces that are concurrent. The other option is for three forces that are parallel. So if you have a body and there's one force acting this way, to balance it out, you could have another two forces that are going in this direction. Okay, and you can see that all of those forces are parallel. Okay, you can't have them not parallel. So that's the other rule. So in this purple box here is our three-force rule for equilibrium. And if a body is in equilibrium and has three forces acting on it, those forces must be concurrent or parallel. Okay, something to remember. A little bit of information about solving this type of problem. When solving three-force rule problems, it is essential that you must first establish there are three forces. Okay, so you need to find those three forces. Often the third force will be the reaction force. Okay, and they won't show it. Okay, if you forget one of your forces, you're going to get the wrong answer. Anyway, hope that helps. Make sure, like I said, you get all of this information down, and we'll now go on to the problems on this page. Watch the other videos about these ideas as well. They'll nourish the concept, and then we'll do some three-force problems. There's also a video on three-force problems on the page as well. And so by the end of this, you should understand the three rules for equilibrium, and you should be able to do these types of problems for systems that are in equilibrium, three-force problems. And you'll be using all of this information later on when you do more advanced problems involving moments and all that sort of stuff. Okay, we're on the steady road to an understanding of physics. Just like I said before, we've already done things like breaking an inclined force into its components, calculating sums of vectors. Now we've got three-force rule of equilibrium. All of these things you need to understand fully. Line of transmissibility, you'll need to understand all of these concepts so that you can move on to the more complex stuff. So I'm hoping that you're taking copious amounts of notes, and that each time you've introduced to a new concept, you're going home and making sure that you understand it and asking questions if you don't. See you next video.